So I'm going to talk to you today about the basics of CMR and the basics of Fluorine 19MR. And I have quite a few things to cover. For many of you, this will be very well-known territory, so you can nap a little bit longer if you want for the first bit. But then you really have to wake up for the second part, because that's where things get really interesting. So I'll start with, of course, the most important part of cardiac MR, which is motion correction. And I got most of these slides ages ago from Matthias. I meanwhile modified them heavily and so on, so any mistakes are without a doubt mine. So this image you might have seen also several times before. This is one of the first MR scanners in the world on the left from Aberdeen with Bill Edelstein next to it. And on the right, you don't see a funny tapestry or something like this. This is one of the first cardiac images, or even the first cardiac image that there was. And if you look on the left and the right, you can kind of see the arms, and you can see the chest quite easily. But the heart, of course, is completely blurred. So for imaging the heart, this was not really a big success yet. However, if you would repeat this now in one of these modern, very fancy $1 million MR scanners that the companies build for you these days, and you just acquire an image of the heart, what you get is the image on the left here. So not that much better, to be honest. And where we want to go is something like this here, the image on the right, where you can nicely see the coronary arteries aligned. So we need to correct a lot of motion to get from the left to the right image. And why do we need to do it? Well, there's several types of motion that affect the heart. There's intrinsic cardiac motion, which is caused by the cardiac cycle, of course. It causes a movement of about 2 centimeters. There's extrinsic motion, so the respiratory cycle, so 12 breaths per minute or something like this, also 2 centimeter motion. And in many applications, unfortunately, the MRI data collection period is quite long compared to this motion. So we need to do something else than just acquire fast. Because if you just acquire fast, like you can see here on the right with an X-ray angiogram, then we don't need to correct for any motion. Here the frame rate is sufficiently high, and each frame is completely acquired, that during this frame basically there is no motion. Well, that works. But if we do use things like stronger gradients, shorter repetition times, parallel imaging, compressed sensing, etc., then we still are not at this level with MR yet. So we often, especially if you want to do mapping or 3D acquisitions, we have minute-long acquisitions still. And of course, if we do these things above, we run into things like nervous stimulation, RF deposition, and strong acoustic noise as well. So we want different solutions. The most well-known one that, of course, you all know is ECG triggering. And here, essentially, you combine a trigger from part of the ECG waves, or part of the ECG signal, so the R wave, the big peak you see in the middle, together with K-space segmentation, and you collect a small bit of data each heartbeat. And that is, of course, during minimal myocardial motion, either in the endosystole or in the mid-diastole. And after you get the complete K-space, you Fourier transform it, and tada, you get your picture out. But this, of course, necessitates reliable ECG signals. Now, if we just use ECG and let the person breathe freely, we already go from this uncorrected image to this. So just K-space segmentation, you still see some artifacts, and the coronaries are not very clear yet, but you get a quite big improvement. So this is really the main, the workhorse of motion correction, essentially in cardiac imaging. It's ECG triggering. Then we also need to get rid of that respiratory motion. And this can be done a whole bunch of ways. You can do averaging, so you just acquire your signal multiple times, and your motion artifacts from respiratory signals will just average out. You can use respiratory bellows, so a belt around you, and then use the signal from this belt to guide your acquisition. You can just hold your breath, and you can use navigators, so you can use some kind of MR data. Breath holding has a lot of advantages. It's easy to implement. It's not vendor specific. It has short scan time, or you can use it for short scan times, and it keeps your scan times short. And so it's preferred for fast 2D imaging. So things like function, perfusion, scar, and so on. However, breath holding has some disadvantages as well. You can see the drift here over a single breath hold. It has some repeatability problems. Here you see a scan that consists of multiple breath holds, and these don't really align. So then your images also don't really align. And so it has some disadvantages as well. The single breath hold duration limits the spatial resolution. You get the diaphragmatic drift that I showed before, and this misregistration of multiple breaths. And of course, you have a lot of operator-patient involvement. So you need to really tell your patient that your patient needs to understand you, needs to speak the same language at least, and needs to want to work along. So the first solution for that was the lung-liver navigator. So you track the displacement of the diaphragm. So if you're acquiring the image of the heart over here in this image, then you place, for example, here an extra navigator on the side. This is a 1D acquisition, as you can see on the right here. It goes very fast at the moment. Normally it's not this fast. But as you can see, you have basically an acceptance window in green there. And only the data, or only when the navigator or detection falls within this green window, then you will acquire data. But this is basically the transition from the lung to the liver. So lung is dark, liver is bright signal. This is very simple for any even older computer to detect. And so you can really inform your acquisition based on this. It has several advantages. The breath hold quality doesn't govern the image resolution. You can just keep on going and acquire very long scans. There's no operator or patient involvement, so even that patient that speaks another language is fine. And then it's flexible for high resolution 3D acquisitions, etc. And it has been demonstrated in a multi-center trial by Matthias and friends a long time ago already. So going from this uncorrected to the ECG triggered image was this transition we saw before. And now if we move to navigator gated, now all of a sudden the coronaries are very bright and sharp. So yeah, we're good basically. We've corrected for most motion. There are some drawbacks though. We really need that lung-liver interface to be exactly within the acceptance window, so you have a very limited and unpredictable scan efficiency. The patient can change the breathing pattern, can fall asleep, for example, and all of a sudden he doesn't go into that acceptance window anymore. You have an infinite scan, for example. There are some temporal delays and hysteretic effects. So as you can see in the diagram on the bottom, not all people breathe in and breathe out the same way. And that changes the relation, of course, between the diaphragm position and the position of the heart. Placing this navigator, which is sometimes a crosshair or sometimes a dot and so on, that needs to be in a very exact position, is a relatively complicated planning for the technicians, so they don't like it either. And it's of course a point that goes wrong. Each vendor has their own solution for this as well. And most famously, there is an empirical factor of motion between the diaphragm and the heart. So basically, there was a paper a while ago that over a large group said the relationship between the diaphragm and the heart movement is 60%. If the diaphragm moves, then the heart moves by 60% of this. And everybody took this value for granted, basically, and has been used ever since. And of course, patient bulk motion is still not accounted for. So one next step was the respiratory self-navigation. David will probably tell more about this tomorrow as well, where you can use, for example, there are many types of self-navigation, but what you can do, and what is done in Lausanne a lot, we can use a superior, inferior readout, so a single readout, and track this signal basically and correct your data through cross correlation with this. So for this, you need to do a few manipulations as well of the data. So you need to make the heart stand out quite well. So you select, do some coil selection, as you can see over here. And then essentially you can follow the blood pool over time. And now you can just align basically all these little segments with the signal that you get here. And the nice thing is here you have, that you have really 100% efficiency in your acquisition, because you don't need to wait for things to be accepted anymore. All data sets, all bits can be used. And of course, there are many different techniques that did similar things to self-navigated data. Finally, there's also bulk motion. So when the patient really shifts and so on. So non-cyclic motion, what people that study the brain often look at, right? When they just turn the brain once and so on. And this is very hard to separate from cardiac and respiratory motion. But it's good to remember that it exists also for our more cyclic motion-oriented motion correction. So basically, what we do in cardiac MR is to inform the patient, just don't move. And indeed, we limit the mobility, so we strap them in quite tightly and so on. And of course, we just limit the scan duration, so there's less time to move. and we maximize the patient comfort. So that's it about what I wanted to tell about the basics of motion correction. So that's, now that we know this, and that this is the most important thing, the motion correction, we can look at changing contrast. And that really goes as a function of the motion correction. So if we need to acquire as fast and robust as possible, and we can only change the contrast as a function of this, at least in most cases, everything becomes kind of building blocks. So what we do is we have this fast, robust acquisition we see on the right. We have a navigator perhaps in front, and then we add some Lego blocks basically to generate contrast. So here we have the timing of the ECG. So the red arrow is on top. So this stays fixed, and then we adapt our contrast generation next to this. So this can be many things. As you can see here, the contrast can be generated with inversion recovery, saturation recovery, T2 preparation, fat saturation, etc., etc. But you all do kind of the same thing. They take the timing of the motion correction and so on into account, and then add on this contrast generation. And of course, this can be done with or without contrast agents. Now, just to highlight one or two of them, inversion recovery, you probably all know, is the equation you see there in the bottom. You invert the magnetization, you wait for the recovery of the signal, in this specific case, that's used a lot in cardiac MR, we inject a contrast agent and then exactly wait for the signal of the myocardium to go through zero, and then image the blood pool. So what you then get is going from images like on the left, you go to something on the right here, which is an inversion recovery image post-gadolinium. And the other thing that is used a lot in cardiac MR is functional imaging. Don't let the brain people hear that though, but yeah, still you're measuring function, so it can be called fMRI if you want. But this is indeed used to establish ventricle and muscle volume, inspecting contractility, etc., etc., and results in the images that you probably know well to see in the bottom. So this is, again, a segmented acquisition, but instead of acquiring one little segment per heartbeat, you basically acquire them continuously. So in your first heartbeat, you will acquire the first two lines of the first frame, then the first few lines of the second frame, then the first few lines of the third frame, etc., until you've got a bit of all your movie frames, all your scene frames. And then in the second heartbeat, you collect the next few lines and so on, say, indeed, as is shown here, line 5 to 8 or so, and etc., until your entire case space is filled up. So even though it looks like a real-time movie, it is not. And when you look for artifacts in this kind of image, you need to keep in mind that it's acquired in this segmented fashion. There are two main ways to do scene imaging: prospective, so you wait for an ECG for a fixed number of phases, and this way you will probably miss the end of the heartbeat, or you might skip a heartbeat because you fixed your basically length of the acquisition, and a patient's length of heartbeat always varies. Or you can do it retrospectively, so you just use whenever a new ECG trigger comes in to switch to the next heartbeat. However, this needs quite robust ECG triggering, essentially. Then finally, the technique that I want to discuss is tissue quantification with cardiac MR, which I do myself quite a bit. There are many flavors of this again. So you can do spectroscopy, which characterizes something in the tissue. Do you want to do mapping, T2 star mapping, etc., etc. You can quantify diffusion, chemical exchange, and so on and so on. I'll illustrate things a bit with T2 mapping, which I'm most familiar with, but all the other ones are indeed, they work along similar mechanisms, except perhaps spectro. So if you normally have weighted imaging, what I showed before, essentially, so right, black and white grayscale images, they have some disadvantages. They're qualitative. The signal varies a lot. They can be misinterpreted easily due to artifacts. And so there's really a need for mapping. Even if you're not that interested in the quantitative values, you remove a lot of these variabilities that you get from weighted imaging. So the relaxation times only depend on field strength and physiology. And it can be compared between patients and sessions because you get numbers. So how does it work? you essentially increase the time when the magnetization is transverse several times, and then you fit the signal loss in each pixel. This is classical mapping, essentially. So you do, for each pixel, you map, for example, with T2 mapping, the signal against your echo time, and you get an exponential decay, and in each pixel, and now you take this value out to T2 here. These days, of course, there are many variations and advancements on this, but this is how it tends to work. Here's what I used to do, still do actually in the heart. You do some kind of robust imaging, so spiral imaging, BSFP or GRE, and combine this with a variable T2 prep. So we have a very robust. We get just 3 images, we fit these 3 points, and we get a nice colored map out like this. So the take-home messages from this intro to basic CMR are indeed that you always need robust motion correction for cardiac MR or cardiovascular MR, and that's really the basis of most imaging sequence, the first thing you need to think about. Then you can start thinking about generating contrast, but only then. The scene imaging that I showed is the most widespread cardiac MR technique, and many tissue parameters can be quantified at the cost of time. So now I want to switch gears and talk us briefly about fluorine MRI. So far we've been talking about anatomical imaging, so that's non-invasive, images abundant water. You have a very high MRI sensitivity, the highest gyromagnetic ratio of all nuclei, and you get contrast to chemical and magnetic tissue differences. But you can also look at other nuclei, carbon, nitrogen, oxygen, etc., and amongst them fluorine. So fluorine 19 is not fluorine 18, that's used for PET, right? That's radioactive, etc. Fluorine 19 is completely stable nucleus, and there is no natural fluorine 19 in the body that you can detect with MR. There's some in the teeth, but that's fixed and bound, so you can't detect it. And it has 85% of the sensitivity of proton, so which is the second highest, basically after proton. But so since you don't have natural stuff in the body, anything that you do inject basically is your contrast, essentially. So anything that you see here. So Matthias gave me this image ages ago from some guy that did something in Italy a while ago. If you add fluorine MRI, if you would inject fluorine, you would get a signal like this. So much easier what I do, very simple images. And then, of course, you would overlay the two of them, and then you would have your localized signal. Now, why do we want this? Why do we want to inject anyway fluorine? So this brings us back to James Cameron in the 1980s. I don't know if you ever saw this movie, The Abyss. They go deep sea diving, and then they say the pressure is so high that you can't breathe air anymore. You need to breathe liquids. And these liquids are basically perfluorocarbons. And that's actually real. Here you see a mouse basically breathing in perfluorocarbon because perfluorocarbon has a higher concentration of oxygen per volume than even air does. So this overcomes the partition coefficient for the lungs and so on. It's also, of course, then been picked up by cyclists because, of course, why not? Cyclists use this as blood doping. And the molecules look like the one you see there in the middle, so highly fluorinated. So all the hydrogen's been replaced with fluorine. People have also played this as a blood volume expander. So they've injected up to 0.5 liter in people already as a blood volume replacement after traumatic blood loss. Here you see more of these molecules, what they can look like. You can also do very targeted imaging with it. So you can attach some targeting ligands. You can add fluorescent probes as well to the histology afterwards and so on. And what I'm always interested in is this injecting the perfluorocarbon emulsion, seeing that it's taken up by immune cells, then having these immune cells travel to some site of inflammation, and then waiting for it to be cleared from the blood, which happens in a day or so. So you inject it one day, you image the next day, and then you image inflammation. Then the really cool and unique thing of perfluorocarbon is that it reflects the immune cell presence over time. So if you see the image on the left here, they injected some perfluorocarbon and an irritant that causes inflammation in the fat pad of a mouse. And then over time, this inflammation went away, the perfluorocarbon went away, and the irritant went away. And as you can see in these curves on the right, they really nicely show that you can use fluorine MRI to track inflammation over time. So the advantages are that you have no background signal, that the signal is kind of the present perfluorocarbon quantity, so it can be used for quantification. It's inert, so it allows for easy translation. It clears from the tissue over time, so it can be used for monitoring over time. And its main disadvantage is that it really requires special hardware, so you need a fluorine coil, etc. And it has relatively low SNR, so nowhere near as sensitive as PET imaging. Then I want to show quickly a few studies that we did ourselves. Quickly look at the time, so I'll hurry up over there. One of the studies that we did is we imaged myocarditis in a mouse model. So this is inflammation of the heart tissue. And as you see here on the image on the top left, is that even the right ventricle wall, which is very, very thin in mice, gives a very clear fluorine signal when it's inflamed. We also confirmed this ex vivo. Then the histology, as you can see here, you have infiltration in only a small part of the right ventricular wall, but that's still nicely nicely showed up in the images. Then the other thing that's very interesting is even with this disease model, which is a very light myocarditis disease model, you don't get changes in the injection fraction yet, so no visible disease yet, as you see in the bottom right, but already the disease degree nicely correlated with the amount of fluorocarbon that we had present. We did something similar in atherosclerosis, so looking at the inflammation in the plaques in mice. There we could also nicely detect the inflammation in atherosclerotic plaques, both in vivo and ex vivo, and then scan the aorta overnight. Right, the mouse aorta is like this thick or so, 1 or 2 millimeters thick, and then even in the branches we could nicely detect the inflammation. And histology nicely confirmed the presence of these on the co-localization of the perfluorocarbons, which are here in green, together with the macrophages in red, so that the signals become yellow in the bottom right. Now, of course, these are all mouse and animal studies and so on, very interesting, but now we want to translate this to the clinic. So we want something that gives a unique application, that is highly specific and sensitive, needs to be regulatory improved, right? We're going to inject all these perfluorocarbons. So we need a lot of improvements. So first thing we did with imaging was to increase the sensitivity. So if you have a standard image here in the middle, we worked together with Jerome and some people from Siemens, applied some funny combination of averaging and compressed sensing, so undersampling one bit and then using that time to average another bit, and this really improved our sensitivity. We did some optimization of acquisition protocols, etc. So getting the best simple echo times, pull sequences, repetition times, and so on out. And some other people, they did a confirmation in large animal models. So here you have a pig model of an infarction, as you can see with the balloon in the graph on the bottom left. And the perfluorocarbon very nicely lights up the infarcted area. But then if you combine it with LGE, so late gadolinium enhancement imaging, that images the scar, you can very nicely see that the perfluorocarbon signal, as you can see in the bottom graph, very nicely localizes with the inflammation histology and not with the scar histology. So it really gives a separate biomarker. Then we did some characterization together with the startup company in Scotland of a new perfluorocarbon that's already approved. So this can be used in clinics in humans basically the moment we get the documents. And this in turn led to a clinical trial that we've now just we're setting up at the moment. So we're waiting for the last OKs from this perfluorocarbon, and then we're going to study acute inflammation in carotid artery plaque. So we will recruit patients that have had TIAs or strokes, and that will have endarterectomy, so that will have their plaque from their neck taken out essentially. And before that, they will receive fluorine MRI to see what the inflammation load is essentially. And the nice thing, of course, of taking this plaque out will be that we can then do ex vivo scanning and histology and confirm the amount of inflammation and perfluorocarbon that's present in there. So that will be happening in the very near future, end of this year or so. We should be able to start. So watch this space essentially. So in conclusion, everything together, we saw the first 4 things earlier up. Remember, you can't do cardiac MR with good motion correction, and all the other things are dependent on this. But I'd like to add on this from this last part, that fluorine MRI is a unique imaging modality that can be used to monitor inflammation and to track cell populations. Thank you very much for your attention.